right. So yesterday we went through the whole process. We gotten all the way through oxidation, oxidative phosphorylation. We talked about fermentation and anaerobic respiration. Cell respiration. All of these processes are energy releasing. So even though we have to jump start it right at the very beginning, for the most part, these reactions are going to happen spontaneously. And with that little jump start of energy, they're actually going to happen much more rapidly, again, with those enzymes that are every step of the way going to be involved in this process. And this is one huge catabolic set of reactions. So these are catabolic pathways. And glycolysis can accept a wide range of carbohydrates. It doesn't just accept glucose. So we talked about glucose, as kind of glucose is what we use, but we don't really eat very much glucose. We eat a lot of other things. We eat starch, for example. We eat glycogen. We eat disaccharides like sucrose, which is just table sugar. So all those things are going to go in through glycolysis. But in addition, we've got other macromolecules as well. We've got proteins, and we have lipids, and we have nucleic acids, and all of those things are going to go into some part of these catabolic reactions, some part of these reactions for cell respiration, and it happens in different ways. And I just want to talk a little bit about that. You're not going to need to know the specifics on these things. I really just want you to be familiar with the fact that it isn't just glucose. We talk about glucose going in, pyruvate coming out, and then oxidizing that to acetyl-CoA, and then all the electrons get stripped away, and NADH and FADH2 make the ATP. But in reality, electrons are being stripped from all of the foods that we eat. For example, our fats. Our fats are getting digested, and they will be broken down to yield other intermediates in the whole cell respiration cycle, or cell respiration pathway, I should say. So fatty acids can get broken down into acetyl-CoA. Acetyl-CoA is the precursor for the Krebs, or the citric acid cycle. You can also break it down into NADH and FADH2. So where they go in, where the different macromolecules go in is not the same for every molecule, but they all go in to cell respiration, and they're liberating they're having their electrons stripped from there. They're becoming oxidized. Fatty acids, it says here, is beta oxidation. You don't have to worry about that, other than you do need to know you're stripping away the electrons. That's oxidation. You're taking that away. You're oxidizing those foods, and then you're reducing our shuttle carriers to produce NADH, and that will go on, and FADH2, and that will go on to produce our ATP. One thing that is of note here is that an oxidized gram of fat produces more than twice as much ATP as an oxidized gram of carbohydrate. What does that mean? Well, if you ate a tablespoon of butter, that would keep you a lot fuller than if you ate a tablespoon of sugar. There's just more calories, and there's more electrons. There's more bonds, and every time you break those bonds apart, you're releasing those electrons. You're oxidizing that molecule in a fat than there is in either a carbohydrate or a protein, for that matter. Okay. And we see that all the time, right? If you want to be full, you're not going to eat something that is a simple sugar. That's going to be pretty much a recipe for a big crash. Does anyone have a sugar crash where they eat something really sugary, and then like an hour later, you're like, oh my God, I feel so dead. And the reason is you get a really fast burst of energy, but it's fast and it's gone also very quickly. Whereas if you're eating something that's more long-term, like a complex carbohydrate like starch or rice, or you're eating something with some fat in it, that is going to keep you feeling fuller for longer, okay? Because it's going to take longer for it to digest, and you're going to get more ATP out of it. All right. So all your molecules that you eat are getting oxidized, not just glucose. And this figure shows that you've got proteins. Proteins get broken down into their monomer, which is the amino acids. Carbohydrates will get broken down into sugar. And the fats will get broken down into its two constituent parts, glycerol and fatty acids. And then they go into different parts of the cycle. You do not have to memorize this diagram. This is really just to show you that all of your foods are going in somewhere into cell respiration. They're either going into glycolysis directly, or they're going into, they could be made into intermediates and go to Krebs cycle, or they could have their electrons directly stripped away, and those NADHs and FADH2s can go to the oxidative phosphorylation. All right. When all this happens, we're releasing ATP in these steps, and we get 32 molecules, more or less, of ATP every time we digest a molecule of glucose. From that catabolic pathways, we'll then use those ATP molecules to create bigger molecules. The whole point is that we have this set of reactions that is tied to energy requiring reactions, and that's our anabolic reactions. So our anabolic reactions need energy. It's the catabolic reactions that are going to provide that. So we eat that food to liberate the ATP, and then that ATP will be used to build up bigger molecules. Sometimes our food itself will not have its electrons completely stripped away. And when that happens, it instead will use some of those precursors for building blocks. So we might not break an amino acid down after we eat some beans, for example. We might just break it down into those amino acids and then build that back up into a different protein that we can use to build muscle tissue, for example. All right, Gesundheit. I was just having a conversation with Miss Nelson about this the other day. Our body is really good at holding on to calories. When you eat something, it will be used either for a precursor for something else, or it will be used to make ATP. Or the other thing that can happen is if you eat too much, your body is not going to get rid of it. It's not going to let it go. Instead, it's smart enough to know, I should keep this around, and it will be changed into a form, usually fat, that will be stored. But the body has to figure out, how do I know when to do that? And that is done by what are called feedback loops or feedback inhibition. And that is the idea that when you get to a certain point in the cycle, the body can say, oh, I have enough ATP already. And if I have enough ATP already, I'm not going to continue to make more ATP. One of the things that I don't think I've pointed out so far this year is ATP is a very, what's the word I want? ATP is not a very stable molecule. It only sticks around for a couple seconds. So you've got to use it or lose it. Okay, you can't, and that's why we store things as fat, for example, and we don't store it as ATP. Otherwise, we have big old storages of ATP. But ATP is a very unstable molecule. And because of that, that's one of the reasons we have to release it in this stepwise manner, because if we released it all at once, we wouldn't be able to benefit from that. We wouldn't be able to get any real value from that, because a lot of it would just get wasted because we don't need that much ATP all at once. So we can use that feedback inhibition as a way to regulate whether or not we are proceeding and making more ATP, or we're saving that food that you've eaten for later use. So we can always bring it back out and we can use it later. So there's a couple of different steps along the way. Let me see if I missed a. Not really. So what this diagram is really showing you is a couple of different things. There is one great enzyme. I love this enzyme just because I like the name. It's called phosphofructokinase. Doesn't it roll off the tongue? Phosphofructokinase. And it's an ACE, so it's a enzyme, right? And this is a key enzyme in these catabolic processes. So whether or not glycolysis proceeds is based on whether or not phosphofructokinase is turned on or turned off. And in our last chapter, we talked about how we could regulate. Remember our regulation of enzymes? Maybe. So we can do this thing called, and it's not on this slide, but I'm going to show it to you because this is important, allosteric regulation. Is there two L's in allo? There's just one. Allosteric regulation. And that is where you have an enzyme that has a shape. Maybe you have a shape like this, and it's active at this point. And then there is this molecule that we know of called ATP. And so when ATP levels are high, that will feed back, and I don't think it's ATP directly, but something will attach to not the active site. Remember that little divot there, that little triangle? That's the active site. But it will attach somewhere else, and it will change the shape of the active site. Maybe it makes it more like this. And now it's no longer active because it has the wrong shape. It cannot go ahead and continue breaking things down. So it turns it off. That's allosteric regulation. So that ATP could force this change in shape. And now the molecule, the phosphofructokinase, the enzyme, it can't work anymore. Okay. And so everything after that, all of these steps after that would get turned off. Like, nope, not going to happen. And then that would be the point at which all the food that's kind of queuing up to go forward in the process would get converted into fat storage, where it can be taken out and used later. This last picture in this unit is of that activity of that enzyme. And you can see at low concentration of ATP, phosphofructokinase is going to work much more quickly. No. But you can see it starts off much more rapidly. It still peaks out and works just as fast. This is just saying how fast we get the rate of activity of the enzyme. And if we've got high ATP concentration, it's kind of like, yeah, no, we don't need to go so fast. It's going to take longer to reach that maximum, or it's going to be slower in reaching that maximum because of the fact that you don't need the ATP. You're good. Your body's happy, it's satiated. You don't need to worry so much about making more energy. All right, any questions on chapter 9? Okay, chapter 10, I'm going to talk a little bit about, but not much. Jeez. Haters out there. Okay, chapter 10 is on, so with chapter 9, what we did was cell respiration. And that was a long process of catabolism. Bunch of reactions that their job was to break things apart. Chapter 10 is about photosynthesis, and it's about building up larger molecules. Okay, and it's going to focus on anything that is photosynthetic. Okay? Photosynthesis is the process of taking our energy that comes in from the sun, so solar energy, and changing it into a form of energy that the plant can use. And that form of energy is chemical energy. And they do that with a organelle that traps that solar energy, and that organelle is called a chloroplast. Okay, so when we say chloroplasts, they perform photosynthesis. This is what we're going to talk about, is photosynthesis and how that happens. Directly, if you're a vegetarian, or indirectly, if you're not a vegetarian, photosynthesis is going to feed you. So it says nourishes the world. That is a true fact. If we didn't have plants around, we'd be dead. Okay. We need a few things from them. First of all, what do they make? What do they give off as a byproduct? Oxygen. Okay, they give off oxygen. And they make chemical energy. They make glucose. They make sucrose. They make starch. They make proteins. They make fats. All those things we eat. Okay, we either eat them directly, or we might eat the cow that eats the grass that brought in those energy molecules. Autotrophs are what we call self-feeders. So auto, self, and troph is feeder. They sustain themselves without eating anything derived from any other organism. They will take nutrients from the soil, but they're not taking anything from any other living critter. Autotrophs are what we call producers. Remember from ecology, producers? And they will produce all sorts of organic molecules. Like I said, we're going to focus on glucose because that's how we roll here. But keeping in mind that it's other carbohydrates too. So we could look at starch. We could look at a protein. We could look at even fats. All of those things are being made by these autotrophs. And they're being made from, this is the kind of cool part, it's a symbiotic relationship. They're being made from what we breathe out, which is carbon dioxide. So that carbon, that gaseous carbon, is being placed into a solid form by plants and made into food that they can eat and we can eat as well. It's kind of cool how you can switch states like that from a gas to a solid. Almost all plants are photoautotrophs. Photosynthesis does not just occur in plants, though. It also occurs in algae, as well as there are other, there's some eukaryotes that perform photosynthesis and some prokaryotes that perform it as well. So some bacteria that perform photosynthesis. But where does most of the photosynthesis take place? In plants, but what plants? Or what photosynthetic critter? Or where in the world? Where in the world?
What wilderness?
What is the earth mostly made of? Water. Most of it's happening in the water by algae. Yeah. Because you've got so much water, and that's so much territory or so much land for the algae to grow, and yeah. Heterotrophs. We are heterotrophs. Even if we are vegan or vegetarian, we are still heterotrophs. We're obtaining our nutrients from somewhere else, from some other living organism, be it plant or animal. We are considered the consumers on Earth, or our biosphere. Earth is called our biosphere. Some heterotrophs eat other living things. Others, called decomposers, are kind of a special category. They are a subgroup of heterotrophs. Decomposers are, and their job is going to be to break down dead organic material, or feces. Okay. Why is it that you have to worry about washing your hands after you go to the bathroom? Because you might have poop on them, right? What's in the poop? Decomposers. Bacteria. Ooh, hold on. Oh no. There she goes again. Bacteria. Like E. coli. This is E. coli. Yeah. E. coli had a hairdo. It's supposed to be long and stringy, but I think Rose Lawless, who's over there on my board, she decided to give him a little makeover. But that's E. coli. So in your fecal matter, there is little prokaryotes like bacteria, like E. coli, and they're consuming the food that you didn't eat, or the food that you ate it, but the food that you didn't use. Okay, so that's I have to be careful about that. Almost all heterotrophs, including humans, depend on photoautotrophs both for our food and for our oxygen. Right, we get the oxygen from them, and we get our food from them, either directly or indirectly. A little E. coli. Ooh, sad face. Don't worry, I'll bring out penicillin next time. Maybe. Hey, I'm gonna stop there.